morning. Okay, yeah. So, okay. First of all, the slides today I will use it are available on our course website. It is not in the e-learning system because I will revise the slides after the course and upload to the e-learning system. But however, currently it is only available on our course website. And after the course, I will also upload the video recording. So if some of you will be unavailable in the course, you can watch the video of the video recording after the course. Okay. So let's get started. And today I'm going to introduce computer vision. Okay. And I remember you took the course already, right? So for you, it should be relatively easy. Okay, and in addition, if you are interested in more computer vision or I should say there are some video recording available on the course website. So from my course website, you can see this is a computer vision previous year, 2023. Okay, so there are many topics and the slides and the video recordings all available. There are even some term project. Okay, so two of your classmates also contribute to the course project, right? And this is the courses. That's the academia year, and this is the course website of computer vision this academia year. So there are some ongoing courses and some existing courses, right? Okay. So if you are interested you can download those websites and those slides and watch those video recorded. This is ours, right? Okay. Okay. Then let's get started. Okay, so this is our course website, and you can download the slides we will use today from this course website. Okay, so if so, then let's get started. First of all, okay. So I want to introduce myself first. Okay, this is my brief, I should say, experience. Currently, I am assistant professor at CGU, and before coming here, I was a postdoc at the IOC Center at NTU, and then before that I got my PhD degree from UC Merced, and I was once an intern at Google and Siemens Research, and before that I was a research assistant at Academia Sinica, and I also worked as an engineer at two companies at Hsinchu Science and Industry Park. One of them is AirTech. AirTech is a digital camera manufacturer, and there was a IC design house inside the corporation. So at that time, I was doing, so during that period, I have the experience of how to develop or make digital camera. And before that, I was a software engineer at PixArt. PixArt is a company, it's an IC design house focusing on developing CMOS image sensors. And so I should say, for CMOS image sensors, there are two categories. One is the generic one. It can be used for VGA webcam or for any I should say consumer products. And another type of CMOS image sensor is the specific used. For example, your optical mouse. There is a CMOS image sensor inside the optical mouse. And the CMOS sensor will combine two features. One is sensor, another is a controller. So for such a specific CMOS image sensor, the company, for example, PixArt, it produced 80% of the CMOS image sensor used in optical mouse for the whole world. Okay, so it is a hidden Japan in Taiwan. All right, and this is the list of my published paper. When I was a PhD student, my research topic is image super resolution. So you can see from ACCV10 to CVIU 17. I totally published 6 papers, totally focused on single image super resolution. And during my postdoc years, I help those master students to publish their own papers. So the topics, there are various topics. Some students worked for GAN, some for facial action recognition, and some for image caption. And my research topic for my postdoc was a mobile robot using ASUS Zambo to generate a video summarization. Okay. And recently here. Okay. There are 4.5 years I focused on stock investing. And that is an research topic really interested me. So, okay. And after figuring out those questions, now I come back so that I help a new group of students to publish their paper in ECCV, that is action recognition problem. Okay. Therefore, you can see my experience mostly focused on image processing. So there are a wide range of computer vision topics, and when you read our textbook, you can see, okay, but my experience only focused on image processing. Okay. So if you if it overlapped with your research topic, I will be very glad to help you. Okay. All right, and let's talk about the top computer vision conferences. So the best one is CPR. I think most of you know it. Okay, and how to measure the importance or impact of a computer vision conference? Usually we will use H5 index. H5 index means when a paper was published within 5 years, how many citations the paper will have. And we can calculate the average number for those papers published in a conference. So CPR gets the highest H5 index, more than 400. And there are some, I should say, CPR, ECCV, and ICCV are the top 3 computer vision conferences. And CPR is an annual conference. ECCV, ICCV, and ACCV are biennial conferences. And there are some related region. For example, NIPS. Okay, it is a conference focusing on neural network. It becomes more and more important because neural network is a tool widely used by computer vision researchers. So if you read some papers, you will find some of them are not published in CPR, but they are published in NIPS. Also, there are 2 important machine learning conferences. One is ICLR and ICNL. They are, I should say, 2 competitive conferences, and both of their qualities are very, very high. And there is also an important, I should say, long-standing conference called AAAI. AAAI focuses on AI, and computer vision can be viewed as a part of the AI. Therefore, some paper, if they got rejected from CPR, they would try AAAI. So that's the case. So if you see this, when I and the student once published a paper in AAAI, the reason is just it got rejected from CPR. Okay. Right. And there are some, so this is the winter workshop of computer vision. It is also sponsored by the CVF Foundation. The BMVC is British Machine Vision Conferences, and the ICIP is International Conferences on Image Processing. So there is a relative type. ACCV is the Asia Conference on Computer Vision. As you can see, the H5 index gradually decreased. And FG, it is a domain-specific conference focusing on face and gesture recognition. Okay. Or when I say a decade or 2 decades ago, when CPR focused on pattern recognition and the FG focused on facial and gesture recognition, okay, they have two different audience group. But currently, CPR growing larger and larger, and so therefore, many papers are absorbed by CPR, and therefore, although we still can, they are still the FG conference, it's become relatively smaller. Okay, let's see a trend. So this is the CPR record from 2011 to 2024 within the 13 years. This is the audience attending the CPR conference from less than 2,000, and it continued growth than 10K. Okay, and this is the submitted and accepted papers by CPR. So here you can see in 2006 there are only, I should say, several hundred papers accepted, and this year there are more than 2,700 papers accepted and more than 10K papers submitted. So it's a huge increasement during those 2 decades. Okay, so this is the topic, I should say categories of CPR 2024. So you can see the hottest topic this year are image and video synthesis and generation, and 3D from multi-view and sensors. Okay, and okay, so there are the numbers of the accepted papers. So because there are so many papers published just in CPR, and there's also another conference, ICCV or ECCV. So we can say there are more than 4,000 high-quality papers published in computer vision communities every year. All right. So it means there are a lot of new knowledge available every year. So no, I should say, since you are, because you are trying to, I should say, okay, either get those knowledge or just use their knowledge. So you should be familiar with how to find their papers. The easiest, okay, there are two popular ways to do it. First, you can use IEEE Explorer or some Google Scholar to search papers you want. But however, for example, if you use IEEE Explorer, one of the problems is our school doesn't pay for it. So you cannot download papers from IEEE Explorer. Okay. However, there are some papers available at archive. Okay. Sometimes the contents are the same, but we cannot guarantee. However, if you want to find a paper published in CPR, ICCV, or WACV, okay, there's another organization called Computer Vision Foundation. It supports the 3 conferences. So you can see every year they will upload all conferences to this website. And once you go to the website and just key in the keyword, it is very easy to download the full content of the paper. Okay, so now let's talk about our textbook. Our textbook is this one. It is the Algorithms and the Application for Computer Vision, the 2nd edition. Okay, you can download this PDF the PDF version of this textbook from Selesky's personal website. It's free, totally free. Okay. And who is the author? He is Richard Selesky. He was the professor of Washington Computer Science and Engineering Department at University of Washington. But however, he has retired already. And he also was a researcher at Microsoft Research Seattle. Okay, and he also quit from there. Now he is a researcher at Google Research, also at Seattle. So let's take a look of the content of this textbook. It covers a very, very wide range of various topics in computer vision. Okay, so this is the just the content. Okay, so let's make a quick summary. There are some basic chapters. First, introduction. It talks about the history of computer vision, and the second, the fundamental of computer vision is how do you generate images. So in chapter 2, it talks about the image formation. And the third, once we have images, can we use those images to solve some computer vision tests directly? Maybe yes or not. So there is a fundamental step. It is called image processing. We need to refine or clean, or just for example, if there are a lot of noise in an image, how to remove those noise. So it is the basic step or necessary step up to the quality of the image to process it. So the chapter 3 is also the fundamental or basic chapter for computer vision. And chapter 4, it is a model fitting optimization. Because when you are going to handle some slightly advanced computer vision task, alright, you are dealing with some machine learning problem. And you need to find some way to optimize your model or use your model to fit in some computer vision problems. Therefore, chapter 4, you can treat it as the introduction to machine learning or model fitting or optimization. And chapter 5, deep learning. So let's take a look. So this is the second edition. What will be the first edition? Yes, you can find or download his first edition from internet or from some libraries. It's fine. And once you compare the first edition and the second edition, you will find the major change is chapter 5. So his first edition was published 12 years ago. And at that time, deep learning is not so important because now it's 2024. And 12 years ago is around 2012. What is the important event happening in 2012? The AlexNet. It was just released. And actually, it shocked the whole computer vision community because it is so powerful. So within and our textbook was published in 2 years ago, 2022. So within the 10 years, he observed the importance of neural networks gaining more and more attention. So when he organized his second version textbook, he removed some old, less important topics and insert the deep learning chapters in chapter 5. And I assume, okay, you have the basic knowledge of deep learning because you took the 5 courses lectured by Professor Wang, and his topic is deep learning. Okay, and okay, so may I ask a question? When you okay, does Professor Wang's topic about the deep learning covers some computer vision topics. Okay, so let me say there's some architectures mentioned in his slides. For example, AlexNet. Yes. ResNet. Yes. Okay. And for example, UNet. No. By name. Okay. Okay. Fine. So, all right. So, for example, AlexNet. Why was AlexNet released? It is going to solve the image classification problem. And why is also ResNet was released? The same image classification problem, but they were released in different years. AlexNet was in 2012, and ResNet was in 2016. Okay, so AlexNet is the first one, and every year there are new architecture proposed, and they show improvement year by year. So in 2016, ResNet, okay, and this amount the importance. There are only 8 layers in AlexNet, but in ResNet there are 152 layers. So how to make the breakthrough to increase the number of layers? Okay, of course there are some reasons, and the ResNet show, okay, if they try to learn residue rather than signal, okay, they can increase layer and still reserve the gradient so that it will not vanish in the network. Okay, let's go back to our slide. And in chapter 6, Selesky talks about some major or some, I should say, everyday computer vision task. This recognition. It covers 5 topics: image classification, object detection, segmentation, and video understanding, and vision and language. Okay, so that's the reason. Let's take a look of our course website. That's the reason why I list classification, segmentation, and detection here. Because I think, I assume, because it is an everyday recognition, computer vision task. So I assume you may be interested in it, but maybe my assumption is incorrect. So please let me know what you are interested in so that I can prepare my slide for it. Yes? Yes. Yes. Yeah, take a look here.
I think this has never been discussed, right? Do you know? I mean, you know?
No, I think they don't know before this course. Okay. So let me explain here. Since KJ raised a very important question. Okay, so I'm wondering how to grade you. Yeah, this is important because everyone you need to have a grade at the final. And our course is separated by 3 sessions, right? And okay, could you let me know how do the other professors grade you? Okay. Okay, so is this a paper exam or online? Okay. Okay, it is something similar to the paper exam. Yeah, similar to. You need to answer many questions. Okay. And how about Professor Gu? how to grade. Okay. I personally don't like paper exam. I personally don't like it because for me, those knowledge are available in the textbook. You can, of course, memorize that. It's good. But for me, it's unnecessary. Okay. If you can find the knowledge you want on time, it's great. And when you see the textbook, there are more than 700 pages. Okay. So I personally prefer you share some knowledge with your classmate to help them learn something they don't know. Okay, so this is my plan. So how to do it? My plan is you can present a paper, okay, or you can take a mini project, okay, so that you can share the domain knowledge or your specific knowledge with your classmate to help them learn. So this is my plan. Because of the plan, so okay, if you want to do a mini project, sometimes you need some collaborators. So you can find your classmates to do it. Okay, and how to grade? This is the key issue. Well, I will use the criteria, the knowledge your classmates gained from your presentation, and I will contribute 80% of the grade, and the remaining 20% will be your peer grading. But however, the plan, there is a limitation of this plan. It means on the last day, every of you need to come to the classroom. I don't know whether it's feasible or not. Okay, so finally, our presentation day is November 20th. Why do I need to record? December 12th. Why do I need to require you submit your slides 1 week earlier? Because I want to read it. So that if I found, okay, I can give you some feedback, okay, I will do it. Okay. Of course, after you submit your draft, you can modify it. Of course, that's fine. I just want to know, okay, what paper you read, okay, what mini project you did, okay, because we don't have a pitch during in the following weeks. Okay. So okay, now let's go back here, and from chapter 6, there are some remaining chapters. All of them are domain-specific computer vision topics. For example, feature detection and matching, imagery alignment and stitching, motion estimation, computational photography. Okay, so those are domain-specific topics and domain-specific knowledge. You may not use them in your life. However, okay, so I will not cover those topics in our courses. And my personal, my PhD research topics belong to chapter 10. It's just a very thin slice of the textbook. Okay, and so slang. So do you know what is slang? You know? Okay, never mind. Then, do you have a vacuum cleaner in your home? Yes. Okay. The vacuum cleaner, robot will move somewhere and swap your floor. And how do they know their map? How do you know the layout of your room? Okay, it's just the slant. When it moves, it will if it has a sense lidar, lidar. Okay, lidar or lidar. It will keep sensing the structure of your world, and when it moves, then it will create a map. That is slant, right? Okay, and the depth explanation, 3D image vision. Okay, fine. So you will find a figure in our test, figure 1.12. Okay, so this is the suggested course plan. So from 2 to 6, this is the basic group. And from 7 to 14, they are domain specific. So we will cover this fundamental part. All right. Okay. So let's talk about the property of our textbook. This is the example page. Okay. From the example page, you can see there are a lot of references. So let me enlarge it, please. Okay. So here you can see those nan and yes. This just means a paper. So you will find a lot of references from our textbook. Okay, and there are pros and cons. And the cons is if you want, you can read a lot of papers and gain their knowledge. But the problem is also it takes time and effort. It's not so difficult. It's not so easy to fully understand those. Okay, so the properties of textbook, it provides many high-level introduction. So you can use the textbook as a reference book. If you want to know some topics, just read the text, and you can get a high-level introduction and get a concept. But if you want to dive into the detail, okay, since there are so many papers, you can just pick some of them and try to read it then. Okay. So that's the property of our textbook. So there are no step-by-step detailed explanation, no. Okay. High-level concept. All right, so we talk. Okay, so now let's talk about what is computer vision. So this is the first photo showing our textbook. It is used as an example. Of course, this is a flower, and for human, you can easily recognize where is the foreground, where is the background. Of course, the foreground is a flower, right? No problem. And the background, there are many trees and bushes behind. For human, it's very easy to recognize it. But how to for a machine? How do you develop an algorithm and using a machine to do it? So that is the core concept of computer vision. You want machines can do something as well as humans. Okay, and there are many other kind of vision tasks. So this is a face detection and crossing detection, and this is the object segmentation, and this is a 3D motion construction and structure from motion. And also, if you have some images, how to create the 3D models from those images. This is also a computer vision topic. Okay, so the textbook shows us some interesting questions. Okay, let me think. What is the vision system? How does it work? So of course, some of you may seen those figures already. For example, this A, there are two arrows, which is longer. Okay, visually, okay, this is slightly longer, but in fact, are they the same? Yes, in fact, they are the same. So it means our visual system, okay, since it's the system, there are some pitfalls. Okay, and for example, in the image B, so there are two blocks A and B. Which is brighter? Visually, B is brighter. Do you think so? Okay, but in fact, their pixel intensity is the same. If you use some photo editor to get the pixel intensity value, A is totally the same as B. But however, our visual system will tell you, oh, B is brighter because what? Because it is in a shadow. If it is in a shadow and I see this, okay, it should be brighter than A. Okay. And in the figure C, do you see some gray spot on the intersections? Yes, you see. But of course, you will know there's no gray spot. Okay, this is the I should say just a white or gray circle there. And in the figure D, okay, how many red cross in the figure? So from here, it's very easy for you. There are only 4 red crosses. But in this figure, how many red crosses are there? For you, it's relatively difficult to recognize those because what? Because here it is very consistent. So you can easily spot the difference. But here there are circles and crosses, and they are not in regular patterns. So your brain, your visual system need to pay more effort to find them. Okay. So what should I say? We have a brain, and the brain is a result of evolution for more than 1 million years. So okay, we not only use our eyes, but also our brain to recognize those visual tasks. Okay, so from our textbook, you can also see this this chart. This is the active topics of computer vision in the past 50 years. So from 1970 to currently 2024, there are many hot topics year by year. And okay, so there is a quick through of those topics. In the 1980s, the decades, some breakthrough was made. So for example, from this figure, it has been pyramid blending. So in the left part is an apple. In the right part is orange. How do you combine an image of apple and the image of orange together? And your visual system won't see obvious artifacts. Okay. And also detection. For example, this is a figure of a square and a circle. How do you detect the edges in this figure? Right. In the 1980s, okay, there are some breakthrough in those topics. For example, B, it means depth estimation. And you want to, if you have 2 cameras and they capture images from the same site, and you want to use the 3D, the triangles, triangulations to estimate the depth of those objects in the scene, how to do it. Okay. And also face tracking. So you can see there are many landmark localizations on the face. And image segmentation. So this is the given image. There's a tiger on a wall, and at the background there is a river. How to, so for the same as the flower example, humans are very easy to recognize, oh, this is tiger and this is a river. But however, how do you use computers to do it? So this is the generated result. You can see the tiger. Okay, also you can see the shadow. Yeah, okay. So year by year, there are many new, okay, in the 1920s, so it means, for example, this is the image synthesis. This is the human faces. But here you can see a lot of cottons on the face, but you still see the structure. Okay, and this is the recognition. They want to know, is this a bicycle or not? It's just similar, a question of classification. And this is interactive tone mapping. It means you can create some strokes, and then it will create the tone, something like a colorization. All right, okay, let's take a break for 10 minutes. All right, so in the 1980s, 10 decades. So see, here is the emerge of convolutional network. So this is the AlexNet. It was released in, actually this is the figure of AlexNet. It was released in 2012. And then many researchers in computer vision found that neural network is so powerful and useful to address many computer vision problems. So they use neural network everywhere, almost everywhere now. And without neural networks, some I should say, okay, neural network has been approved very, very useful. Therefore, almost everyone in computer vision today cannot have no knowledge about the neural network. Okay, so once they found the tools so useful, they will try here, try there, and try there, and they solved many problems. I should say, not solved. They make significant improvement on many tasks. For example, segmentation and host estimation. And this is the VR and AR, and even some real-time 3D map creation. Okay, so let's think why they are so significantly improved in the past decades. The reason one is we have more powerful but cheaper computing machines. So let's take a look at this chart. This is a year, of course, from 2010 to 2014. And what is the meaning of another axis? It means how many operations you can purchase by paying just $1. So from this figure, you can see there is a significant trend. The computational cost is significantly and gradually decreased. Say now you spend, for example, $1,000, you can buy a laptop. Okay, and 20 years ago, if you still spend $1,000, you can buy what is type of the CPUs you can get? Maybe Pentium 3. And now, okay, it is i7, say i7 and 4100, say. So the computational power, and even now we have more GPUs, and there are some TPUs. Okay, the price, if the price is fixed, how about the computational capacity significantly increased? So because we have more cheaper and powerful machines, we can use them to deal with computer vision tasks. And the second is the population of cameras. So 20 years ago, 20 years, 20, should I say 20? 30 years ago, okay, what is the medium we use to create photos? Film. I believe you still have the experience of using film, okay? And when digital camera become very, very popular, it's around 2004. I think it's around that time. And then, okay, we have cell phone, a smart cell phone. And there are cameras on smartphones. And which year iPhone was first generation was released? 2009. Yes. Okay. So now we have cameras everywhere. So this is a camera put on the car, and this is a surveillance camera. So we have more cameras. So we can easily generate more images and photos. So that's another force to make the more researchers devoted in computer vision community. All right, so it's a related disciplines of computer vision. So we see computer vision, we need image as our input. Okay, so computer vision is related to image processing, and the important conference in image processing is ICIP, as we saw. And computer vision is also related to graphic. So why? Because what does it mean graphic? Graphic means we use a model to generate images. So when you play video games, you are using some graphic models. Okay, and what's computer vision? Once you have image, how do you analyze the image to create a model? So there are two different directions, and of course they are highly related. So some good computer vision papers were also published in graphic conferences, and the best conferences of graphics is CGraph. Okay. And of course, computer vision is part of artificial intelligence. You can find papers in AI, and we use machine learning to solve computer vision tasks. So ICLR and ICNL are two major machine learning top conferences. You can find a paper there. And also, computer vision is a vision problem. It is related to real human visions. So there are some, I should say, papers published in the, I should say, recognitive science. They will cite or use many computer vision algorithms. Right? Of course, NIPS, now it is called new IPS. Okay. It is the algorithm part or the neural network part. So okay, because it is the important tool or approach used by computer vision, so it is also related to computer vision. Okay, now let's think. When you see an image, what is the meaning of an image? So image means it's a projection from the 3D real world to a 2D plane. Okay. Therefore, it is a process of reducing the dimension of depth. Okay. As a result, take a look. So this is an image, and it is taken from a real world. At the first glance, what do you think about this image? Do you think it's a single thing, or it is a mosaic of 4 different things? At your first glance. All right. Okay. So let's see the answer. Okay, it is a single thing. You just slightly change the viewing position. Okay, from here you see it look at the faucet. So you can see this orange here. This is orange. Okay, and this is a sofa. The blue sofa. The blue sofa is here. Okay. Okay, and this is another example. This looks like a globe. But what is it in fact? Okay, it is a yard. So when you choose, okay, so this is another view. In fact, it is a very flat yard. Okay, when you stand somewhere from those positions, you look or watch the yard. It looks like a globe. Okay, and then some example. So you usually see those funny illusion, right? When you so the reason is here. When you reduce the depth, then the 3D world become an image. You can create some very funny. Of course, everybody know this is the Tower of Pisa. Pisa, okay, and of course, so when you remove the depth, the Pisa behind, it looks like it is hosted by this man. Okay, so here, let's see some examples of how an image is created. So this is the simplest model. It's called a pinhole camera. If you have something, okay, and you create a very, very small hole, then the light of the object will go through the small hole and it will become an image on the image plane. And it has been observed maybe more than 2,000 years ago. Okay. But however, there is a problem of the pinhole camera. It means how large the aperture would you set? If you set a very small aperture, then for example, this problem, okay, you will have because light ray, there is an effect of light ray called diffraction, like this. A single light ray, it through a very, very small, I should say, very small range or something, the light will go through different directions because light is a wavelength. Right? As a result, you will get very blurred images. So, however, if you create a slightly larger aperture, the problem is different light sources will be projected into the same position. So you will also get a very blurred image. Okay, so this is a restriction of pinhole camera. Therefore, how to solve the problem? Use lens. The lens can help us to concentrate different light sources into a single point. Okay, so that it can accumulate more input light rays. Okay, so therefore we can control the aperture of the lens, use the blade. So when you set the aperture larger, you will get this result. And when you set the aperture very small, you will get this result. So there is a term called F number. If you, I should say, for some, I should, okay. The definition of the F number is the focal length divided by the aperture diameter, and they will create a different effect. When you use a large F number, for example, say 2.8, then you can easily blur out the background. Why? What's the reason? The reason is many light rays from the background will be concentrated on the same point. As a result, they get burned, just like this case. Okay. And if you use a very small aperture, it looks like a pinhole. Okay, so that the light ray from the background will go through the very small pinhole, so that they will not be blurred out. Right. So this is the result. However, if you use a lens, there is a side effect. It's called chromatic aberration. What does it mean? It means because visible light covers a wide range from 400 nanometers to 700 nanometers. For a single lens, a blue light and a red light will have different light paths. So for a single light source here, the blue light, it will be focused on somewhere in front of the focal length, and the red light will be behind the focal length. As a result, you will see some purple edges between the extremely bright and the extremely dark regions. Okay. So how to overcome the chromatic aberration? Okay. We use multiple lenses rather than a single lens. For example, this one, you will see 1, 2, 3, 4, 5, 6, 7, and this is another illustration. I should say those optical companies, they developed those multiple lenses set to reduce the chromatic aberration. Okay, so now for the high-end digital camera, okay, you will have a very good lens set, and you can control the blend, the amount of the input rate. And for smartphones, okay, there are also multiple lenses. For example, this is iPhone 15. There are 7 pieces of lens. Okay, the same, they want to control the chromatic aberration. No matter for this one kind of camera or this consumer level, the iPhone, okay, they are both type of digital camera. So let's go through the how we generate an image on a digital camera. Okay, there is a scene or the really 3D world. So through its optics means those lenses and the capture. Of course, for the high-end camera, we have the aperture. We can control the aperture, but for iPhone, we don't. Okay, because that once we can control the aperture and we control the shutter time, it means how many milliseconds we will let our CCD or CMOS to absorb those light source, and then we will enlarge our signal through a gain control and convert those analog digitals to digital signals. Okay, now if we just get those images, it's called a raw image. Some photographers, they prefer the raw images, so they can edit or adjust it by itself. But however, for most consumers, they insist to process the raw images into the final photos. They can immediately enjoy or use. So therefore, okay, for a sensor, since a sensor only can sense the intensity of the light rate, how to create the RGB 3 channels? Usually, there is a coding on the sensor. For different pixels, they will use different colors. Now, so the most famous pattern is pair pattern. It means they use two in a 4x4, 2x2 cells. 2 of them are green, and one is blue, and another is red. This is, okay. And you can find okay, let me show you how to, what is the pair pattern. Okay, because I didn't put it on my slide. It is available in our textbook. Pair pattern. Okay, so this is the pair pattern. Green, green, blue, and red. Okay, why? Because every pixel behind the pattern, it can sense the intensity of the green light. So that we can use interpolation, okay, or we call it a demosaic to create an image. It has 3 channels, green, blue, and red. Okay, so this is a demosaic or interpolation part. Of course, there is noise, and we need to denoise. And if we want to increase its sharpness, there is a sharpen step. And there is another step called white balance. So, for example, you see this light. It's relatively bright. And for some people in their house, they use the yellow bulb. Okay, so for different light sources, we want our images looks like good. So we need to adjust the brightness. So that is the brighten balance step. And we will adjust its contrast through gamma. And we will show some example of gamma here. Finally, okay, we use some compression algorithms to reduce the image file size. The most popular one is JPEG, and then there are some other types, for example, PNG or WEBP. Okay, that's fine. So finally, we will get the image. Okay, here I want to show an interesting paper. It was just published this year. Okay. When we see the steps, some people may say, okay, now we have iPhone 15, okay, iPhone 16. It is so great. If the experience of taking a photo, oh, wonderful, okay, good, because of course they have great lenses, great sensors, and powerful CPUs in the cell phone. Okay, it can create a very, very good photos. But okay, for that, they use a low rank, very cheap camera. Okay, and it is mounted on a drone, and they want what they are going to solve a problem. So if you see the lower part, that is the image taken by the camera. On the camera, because it is so small and so cheap, it is impossible to use the very, very great lens set. Okay, so how do they solve the problem? If they they developed a neural network. So that use the neural network, they can reconstruct highly contrast image like the upper part one. So from this title, they want to do lens aberration correction through a network so that they can generate the high quality images for their application. Okay, now we are talking, this is the chapter of the first, chapter 1, the introduction. Now we are talking to the second chapter, the image processing. As we say, the importance of image processing, it is the input data of our computer vision algorithms or task. All right, so the most simplest one is pixel transformation. It means we can adjust the pixels by itself. It is okay. So let's take a look. This is a flower we see, and this is the original input image. We can do what? We can just make it brighter. So in B, compare with this region and the region, you see it is brighter. Why? You just add the intensity with a number 16. Okay, and we can also multiply the pixel intensity by a factor. For example, this is 1.1, so that we can increase its contrast. We can also adjust the gamma. Okay, gamma we will see in a few slides. Well, let's go to the gamma now. So it will not. Okay, so the next, that is gamma. Gamma. Let's explain why we need to adjust the gamma. Because around 20 years ago, the TV, the old TV, there is a cathode ray tube in the, so it is a large, huge TV. Okay. There is a physical property of the cathode ray tube. It means if you control its electrical voltage, but its brightness is not a linear result of the input voltage. It is there is a exponential relationship. Therefore, we need to adjust the relationship. So we use, so it's around 2.2. The mathematical expression is look like. So we need to correct it so that we can see the correct brightness on the monitor. And however, it can be used to adjust the image. So let's take an example. If this left side is your input image, all right? And since we know the equation here, you can control the value gamma as your parameter. Then when you set a different parameter, you will create a different mapping function. Then when you set gamma as 2.2, this will your output images. For some visual applications, the right part may be better than the left part because the contrast is more obvious. Okay, contrast means when you have 2 pixels, okay, their difference is the contrast. Okay, so for example, when you see this region, it is very bright. This is the cloud on the sky. Can you clearly tell the difference? No. But in this image, their ratio or their difference is enlarged. So you can clearly tell the difference from this region and its nearby region. This is contrast. Okay, so this is gamma, and we can also apply a method called histogram equalization. This is the histogram. If you apply the histogram equalization, you will generate the result like this one. Okay, so it means every the darkest pixels are still darkness, but you create a lot of very bright pixels. So there's another method called partial histogram equalization. The generated result is it is a blending between the original image and the equalized image. Let's take a look here. Okay, so how to do it? So given an input image or original image, we can use these 3 channels to create the histogram for its blue, red, and green, and even the white means brightness. And for the blue, green, and yellow 3 channels, we can create its cumulated distribution. So see the y-axis. It is the number of pixels. Then we use the shape, just the shape, create a mapping function. So the mapping function, you can see the shape from figure C and figure D is the same, but the y-axis becomes different. So here it becomes a mapping function, mapping from 0 to 255 from its input 0 to 255. As a result, we use the 3 mapping functions for every pixel in the input image. Then for the brightness one, we will increase its intensity. Okay. So we will generate a result like this. And if we use a coefficient alpha to blend the generated image and its original image, we will generate the partial histogram equalized image. Okay, now we are, we are talking about some basic concept of image. It means color space. RGB is the most widely used color space. Okay, we can treat it as a raw data. So given this image, for example, these are red channel, green channel, and blue channel. So you can see the blue channel is very bright on the flower because it is a purple flower. Okay, so and here this is a lowercase RGB. It is a conversion. It's a ratio of the 3 channels. So the definition of the RGB is written here. Okay. And also there's another color space for L star, A star, B star, and HSU. They have some intuitive meaning for us. Okay, so for hue, saturation, and value, let's take a look here. So what is hue? Hue means if you think, when you see the rainbow, you see different colors. Red, yellow, green, red, pink, purple. Okay. If you think they are continuing changing pixels, you will create a chart like this one, from red to yellow to green to cyan and somewhere. And then finally, you can draw something like this one. It becomes a circle. You can rotate the circle to get your different colors. That's hue. That's a mean concept. That is hue. Okay. And what is saturation? Saturation means some colors are more vivid than other colors. So from the beginning, if you have no, so black, white, and gray, they have no color. Okay, so this is the case. From the center, you can set it is no color, and when a color has a strong saturation, it has become very, very vivid. Okay. So this is a saturation rate. And also there is a value. Value just means brightness. So here, if the value is very, very small, then you get the dark color. And the value is large, you get a white color. So this is a model to interpret colors. So this is the HSV model. However, from this model, there is an assumption. It means when you increase the brightness, it won't affect your color. So is this correct? Some people may disagree with it. So they propose this another color, means HSL. They change the value to the lightness. And the major difference, when you increase the brightness, you assume you will also lose the saturation and hue. So from here to here, at the top range, you see all of them are white. Okay, it makes some sense. When you see something very, very bright, can you still sense its color? No. Okay, so there's a difference of HSL and HSV. But however, both models are very popular. Many people will use the two models. And this is an example. Given this image, this is the brightness or the V. So it makes sense. It will become the gray image. And this is saturation. So for what region we see the saturation region? Maybe, okay, there is a blue sky. Okay, so it is, I don't know why it is relatively dark, right? So this is a hue. From the hue, you can see this is a green tree. Okay, the blue sky. And however, for this shadow, it is slightly, I should say, it is more close to blue rather than other colors. So in the H images, you see it looks like a blue region. Okay, and now so let's here. So this is HSV and OHSL. Another is LA star, L star, A star, B star. Okay, that is another color concept. That is the perceptually uniform color space. It means for 2 points in the space, if their distance is the same from here, okay, say, okay, here is a point, here is a point. If their distance, this is the distance 1, and this is another point, this is another point. If their distance 2, if distance 1 and distance 2 are the same, visually or perceptually, we will think the change of those colors are the same. So this means perceptually uniform color space. Right, so how to calculate? Okay, first we need to calculate the y and the yn. So what is y? We will see it later. Okay, and there is a cubic square function, and use the cubic square function and this equation, we will create an A star and a B star. Okay, so who developed those functions? Those scientists working for colors. We currently, I should say, I don't know how those equations are invented, but however, it is accepted by most researchers, right? That's their domain knowledge. Okay, Okay, now let's explain what is Y, X, the capital Y, capital X, and even capital Z. Okay. Okay, let's see, how do we measure color? If you have a color, how do you measure it? We have some terms to describe the red, green, yellow, and blue. What is the scientific way to measure it? Okay, so it was measured in 1931, almost 100 years ago. Okay, this is a CIE, it is a French organization. Okay, so let's see how to do it. First, that's all. On our retina, there are 4 different types of sensors. It is the red cone and the red cells. For rod cell, it can only sense brightness. It cannot sense color. And there are 3 types of cone cell: long, middle, and short. So they can sense different type of wavelengths. So their relative responsibility curve looks like this. And on our retina, okay, their distribution is uneven. For cones, they focus on a very, very small region. Okay, this is the fovea region. And for the red cell, it is distributed on the other regions on our retina. So for those CIE organization, how do they measure the brightness? They create some device look like there's a very small aperture, and we can only see the comparison of 2 light sources through a very small hole. The degree is only 2. So there are 2 versions. The first version is degree is 5. The second version is the degree is 2. Okay, so they try. So once they have the device, there is a board on the center, and one side, okay, there's another light source. Another side, there are 3 different pure light. The pure light is 700 millimeter, 500. So actually, in 1931, they can create the 3 pure light, so that they can do the experiment. Okay, as a result, okay, this is when you use the 3 different pure light to compare the with any light in any light sources, they create this equivalence chart. It means if the light source is say 600 nanometers, then it's equivalent a certain ratio of the red light and a certain ratio of the green light. So, but however, how to explain this region? In this region, okay, here, why the value is negative? The reason is, let's take a look at it. Because this is equivalent, they ask their subjects to measure whether the lights on the left side and the right side are the same. Okay, so they found for certain wavelengths, for example 480, okay, when they projected the 480 on this side, they cannot add any red light on another side. They need to project it on the same side of the 480 nanometers, so that the subject will see, oh, the 2 sides of colors are the same. That's the reason why there is the negative curve. Okay. The reason, okay, what is the fundamental reason? The fundamental reason is our cells on our retina. If you see, okay, some 489 nanometers, it will trigger the red the blue and green cells. So how do you compensate it? The only way is you need to project the red line on another side so that your cells will get balanced. But however, it's troublesome because there are some negative values. So how to overcome the problem? They use a linear transformation. From the RGB, the three curves RGB, use the linear combination. They will create a new measure, a new set of measures variable x, y, z. So this is the y-x, y-z is generated. And the y also has a meaning. It means the luminance or the brightness or perceived brightness. So once we have the x, y, z, they convert the x, y, z to the LA star, B star, L star, A star, B star space. And also, in addition to the x, y, z, there is also xn, yn, and zn. It means nominal white. It means your perception. Because we say there are different light sources. And when you see something, the bright here, and the bright here, or even the white here, in your perception, they are different. So they need to define what is the bright you feel or you perceive. That is the xn, yn, and zn. Therefore, you can you need to have the reference white or nominal white so that you can calculate your L star, A star, B star. So once you have the L star, X, Y, Z, okay, you can project the 3D variables on a 2D plane. So let's say, like the capital, okay, like the RGB, we converted to lowercase RGB. Here we have the upper capital X, Y, Z, and we convert it to lowercase x, y, z. So this is the gamma. You sometimes see it on some products. And here you can see a triangle. And the triangle, what does it mean? It means when you use the three wavelengths, 700, 546, and 433, it means there are 3 points on your gamut. And if you just combine those 3 light sources, you can create any kind of colors within the triangle. Okay? That's the reason why they need to add the red light on another side, because it is red. The red eye is here. If you want to create colors on the remaining regions, you cannot just put your insert your color here. It's impossible because you can only the linear combination of the 3 colors is only remaining in the triangle. So here you can see some small circles here. What does it mean? It means within the region, you will feel, okay, you cannot sense the difference of the color. So there are many different types of color spaces. Human, we can see the whole gamut because of our sense, our eyes. And the sRGB, it is developed by Microsoft and HP. So when you now using your laptop, you follows the sRGB color space. And then there are some different companies. For Adobe, it is the manufacturer of Photoshop. They are professional photo editing, or some printing companies. Okay. They defined their own color spaces. So it looks like this. Basically, it is a combination of 3 primary colors. Okay. And okay, when you want to buy some monitors, okay, you will see this logo, delta E, and some 100% sRGB. Okay, now you know its meanings. It means this monitor can cover the color spaces of 100% sRGB. It means So sRGB is this one. Okay, this one. Okay, you can see 100% colors within the triangle region. Okay, and the delta E means it less than 2. So this is the equation for delta E. It means if you have a very, very small delta E, it means the color you see on the monitor is very accurate based on what? Your file. Because you have a file of images. There are a lot of RGB values on it. When you show it on a display, is the color correct? Okay, so once you see this logo, it means the color is very, very correct. Okay, now we are going to talk about the second important part of image processing. It means image filtering. So we will see some examples there, and let's see first explain what is image filtering. It means given a kernel or just a mask, you will use the mask through a linear combination to generate a new image G. So this is a linear filtering. Because it's a linear combination, so you can see the linear term here. And then there are two formats. One is called correlation. It means and another is convolution. What's the difference? The difference is given a pixel, which coefficient in the kernel you will be used to calculate the filtering. For correlation, say this is the 65, the left top corner will use the left top corner in the kernel. But for convolution, it will use the opposite edge, this one. So from this mathematical expression, you can see this is the summation and the summation. So this is the index of the kernel. But for convolution, it is minus. Okay. So therefore, they are equivalent, but expressed in different mathematical format. So let's see the simplest one. It's main box filter. So this is a kernel. Every value coefficient is 1, but you will divide it by 9 to get the average. Let's take a look. So suppose your F is the input image. This looks like there are some intensity values, 90, 90, 90. And the result of this region, it is the pixel values multiplied by these kernels piece by piece and generate the result. So this is 0, 10, 5, 90 times 1 divided by 9. So this is 90. And this is 20. Why? Let's regard these zeros. 90 times 1, another 90 times 1 divided by 9. So you got 20. So go through AV pixels on the image. So you will generate this result. So this is the linear filtering. All right, let's take a look. Suppose this is the input image, and this is the box filters we used. So this is the generated result. So it will become very blurred. And let's see another example. So this is the sharpening filter. What is it? This is a box filter we see. But if we we use another kernel. This is the 2, and all others are 0. We divide this kernel and this kernel, apply it on this input image. We will generate this result. It looks slightly sharpened. And let's take a full range of it. So this is the input image. Use the sharpen filter. We will get the sharpened result. Okay, so there are some famous filter. For example, this is a Sobel filter. So this is the vertical Sobel filter. Apply this Sobel filter, we will get the result. So what is highlighted in the result? Edge, in particular vertical edge. And for horizontal, we will get the horizontal edges. Right? Okay, let's take a break for 10 minutes. Alright, so let's continue. So once you have the horizontal edge and the horizontal response and the vertical response, it's very easy for you to figure out the edge. So this is the we see the Sobel filter. In addition, there are some other types of gradient filters. So this is a one-dimensional uncentered derivative, and this is one-dimensional centered derivative. And from so we will see their relationship later. So our textbook. This is the figure cropped from our textbook. So there is a concept of a separable linear filters. It means so this is a box filter. We see the box filter 3 by 3, but however here is k by k. So but the k by k box filter, it can be separated as two one-dimensional filter. So the first is this, and then another is vertical. So the kernel k, it is a multiplication of a vertical filter and a horizontal filter. So this is a bilinear filter. So this is a 1, 2, 1, 2, 4. It is this and another vertical filter, like totally the same. And this is a Gaussian filter. Gaussian filter is the same. It can be separable as a vertical and a horizontal filter. And this is Sobel. We just saw it. So for the Sobel, what is the combination of the two factors? One is this, 1, 2, 1, and another is -1, 0, 1. So what is -1, 0, 1? It is just the 1D centered derivative. And what is the another 1, 2, 1? It is the so another is the corner filter. So what is the importance of the separable linear filter? It means, let's take a look at this slide. How do we calculate the result of a pixel? It is the multiplication of pixel by pixel respected to its kernel. So how many multiplication and addition do they need to use? K squared. If a two-dimensional linear filter can be separated as two filters, one for vertical and one for another, how many? And we can apply the vertical first and then the horizontal next. How many computational load do they need? Only 2k. So it can be reduced from k squared to 2k. That's the benefit of using the separable linear filter. So the one mostly widely used is the Gaussian filter. So this is the mathematical expression of a two-dimensional Gaussian distribution, and the sigma here means the standard deviation. That's right, standard deviation. It from the mathematical expression, it can be separated as two one-dimensional Gaussian distribution. And when the standard deviation is small, the square means the variance. The sigma square, the variance is small, then it is a highly concentrated distribution, like this here. And when the variance is large, for say 5 here, then the distribution will become shorter or flat. And when we apply the Gaussian filter on the image with different standard deviation, the result will like this one. So this is input image. When we set the standard deviation just 1, this is the result. There's little difference from the filtered image from its original image. But when we enlarge the standard deviation to 5, 10, and 30s, the image will become very, very blurred. And let's compare. So this is box filter, and this output image we see. You can see many patterns horizontally and vertically here. But if you apply a Gaussian filter, you will not see the pattern, because Gaussian filter it is a isotropic filter. It means for every direction the weight is the same, so you want to see the patterns there. Okay, now let's take another issue. That is, when you apply the filter, how do you handle the boundary? Okay, it means if you apply the filter here, then okay, you apply this filter and convolute or create with this kernel, you will generate the image here, right? So that your image slightly squeezed. How do you handle the boundary? If you want to reserve the resolution, okay? So the approach is padding. It means add some more pixels around the region. So there are 4 different types of padding. One is 0. It means for this region, you just add 0 values here. But the drawback is when you apply some image filters, you will get a dark region like this one, blurred dark region. And another padding approach is wrap. It means you just copy this region to here. Okay, so it means, and you can see you copy this region to here. Just copy the same content around the boundary. But however, there are some problems. You can see they are discontinued here from this region to this region. So what will happen? You may generate some unexpected result along your boundary. Therefore, they have some other approaches. It means clamp. The clamp can let your boundary become smooth because, okay, it means you just extend the intensity from the boundary to its outer regions. So you can see it continues here, here, and here. That's a result. Your boundary will be the same as your input image. And another called mirror. Mirror just the flip from one side for this one. So you can see the pattern here. Flip it here, left vertically, horizontally, and even to the corner, right? So this is your. You will also get the same result as a similar result as the clamp, but however, the pixels on the clamp padding approach, they are all the same. But for mirror, it is not. Okay, so it's different. There's another approach called normalized 0. Okay, and let's see. If we want to use normalized, and the Selesky, our textbook author, he highly recommended normalized 0. So let's take a look at how normalized 0 work. It means we need to use an alpha channel. Alpha channel means you can think it as a transparency. In addition to our RGB 3 color channels, if we introduce the alpha channel, then it means we can it's the weight of those color channel. For example, this one. If you have a source image and you have the alpha channel, then you can extract use your so for alpha channel as 1, this is the brighter region. It means your foreground object, okay, the color is, the intensity is valid. But however, for the boundary, it means although you see the color, it is not totally the same because it is a mixture of the foreground and the background. So here you see some great further. When you have the color channel, you can combine your foreground with any background you want. For example, so from here, for this region, the alpha channel is 0, so that it will become the totally background. And for the boundary, it will become a mixture of the foreground and the background. So the enlarged region like this one. Okay. So this is your foreground, your background, and your alpha channel. Then use the equation like this one. It's just a linear combination. You will get the image. So once you have the alpha channel, then you still use the 0 padding. Like you add another 0 here, but you also prepare alpha channel. When you apply some filter, you generate the blurred boundaries. You also generate the blurred alpha channel. And then you divided the blurred output image by the blurred alpha channel so that you can create a normalized 0. It means your boundary won't be affected by the 0. It will still be the same as its source intensity. Okay, so there is another filter widely used. It's called the median filter. So here, let's take a look of our linear filter. It means a combination of many pixels. Next one. So in your kernel, every pixel is a weight to contribute to your output. But for median filter, it is not. It works in this way. For a patch or a region of intensities, we sort those intensity values and we just get the median value. Okay, so here the value is 90 and we found it median value is 27, so we replace the 90 by the 27. So this is the output result. And where can it be used? Let's see the one-dimensional example. Say this is input, so this is outlier. It is very different from its neighbors. If we use median filter, then it will replace by its neighbor. Okay. But if we use a mean filter or just like the box case, it will be an average of between the outlier and its neighbors. So here you see the value is slightly larger than the median filter. And when we apply it for image, so this is an input image. If there are some noise, and then the type of noise is pepper and salt. The pepper and salt means pepper, 胡椒. Okay. Usually it's black, in particular for the black pepper. And the salt, 盐. So it means the bright, very bright value. So you can see there are black and white patterns on the input image. In terms of value, usually it's 255 and 0. Okay. When we apply the median filter, this is a generated result. Most pepper and white are removed. Looks quite good. Okay. And this is the piece of code of MATLAB. Okay. So the image, it has a name because it's a benchmark. What used by many image processing algorithms is a cameraman. So I add the pepper and the white noise to the input image and apply. So this median filter 2 means 2-dimensional. Okay, and I need to specify how large the median. So here is a 3x3 case, but this is a parameter. I can adjust it. When I try different parameters, say 5x5, okay, and 7x7, so apply to the same test image, this one. Okay, so this is 3x3, looks good. But if you use the filter as 5x5, there's a problem. You can see the face or the camera of the image, it becomes very blurred. If I enlarge the parameter to 7x7, okay, it becomes very, very blurred. Why? Because in the medium field, when we use a larger kernel size, and there are many pixels inside it, it is easier for us to take just something like the average of those regions. However, compared with Gaussian filter, so this is a Gaussian filter with the same 3x3, and I use the sigma as 1.0, so this is the result. Which one is okay? Actually, so we can see the differences. You still can see many pattern, paper and cell here, and you still can see the paper, the patterns here. And even though the patterns in this case, it means when I enlarge the standard deviation, the pattern is less obvious, but there still are those patterns. So there are many kinds of filters available, and there are many kinds of noise in the image. Which one would you choose? It will depend on your application. And there's another very fundamental operation for image. It's called morphology. Okay, so let's see some example. This is a mathematical expression, and let's see examples first, and let's go back to the mathematical expression. So first of all, this is the input. So this is binary, so it is not applied for color images. It's also applied for binary. Binary means it's either black or white. So for example, in this case, this is the original image. If I apply the dilation operation, okay, it means in the corner, if there is any pixel, it is black, then it will be dilated. The boundary will be the diameter will increase. Another is erosion. Erosion means there should be S. S means the total number, the full number of the number of pixels in the kernel. Then it will remain black. Otherwise, it will become white. So erosion, the size of the input image shrinked, and there's a majority operation. It means if there are half of the pixel is greater than there are half of the pixels, then it will keep the same. Opening, okay, this is the result of opening. Here you didn't see the difference, but this is closing. So you can compare this region. It is closed. So what does it mean? Closing means we apply a dilation first, and then we apply an erosion. So this is the result of the dilation. And when we apply erosion on these images, then okay, at the boundary, the pixels also shrinks. But here, for this region, during the dilation, it disappears. Therefore, when we apply the erosion, you will no longer see it. And let's see what's this is the example given by in our textbook. We cannot. It is unclear what is the result of the opening. So I found another examples online like this one. Okay. So this is an example from MATLAB website. So this is a circular image for black and white. So this is circle BW. So since it is circular, it shows opening is used to remove small objects. In this input image, when we apply a kernel as a 40 by 30 pixel square, use opening, then this is our output result. It means only images matching this kernel will remain. So here it will remain. Here, okay, remain. So it removes all narrow edges on the input image. Okay, and the crossing, as the same, the example is from MATLAB. The crossing means it will remove small holes. So the small hole, here is a small hole, this is another hole, and this is one. They are removed, and then the large holes, it remains. What is the application? Okay, so this is an example. This is the finger image, all right? So you can see there are a lot of noise. When you use some finger camera to get the image, how would you and there are a lot of holes. Holes means, okay, let me see, sorry, here, okay. Yeah, can you see the hole here? Within, there are a lot of holes here. Okay, you want to remove those small noise. Okay, and fill in those holes. How would you do? Apply the opening and the closing operation. So you can generate this result. When you have this result, you can apply your finger recognition algorithm to recognize this is whose finger. Okay, so this echoes the message of this chapter. Why do we need image processing? Because it usually is the first step for computer vision tasks. We need a good input image as our data. So this is the right image is a good input data, and the left image is a poor input data. Okay. Okay, so there's another I should say method, okay, in the image process. It's called distance transforms. So how does it work? So given this is also binary input, black is white. For every pixels here, we want to calculate what is the distance from the pixel to its boundary. So this example here is, let me say, well, let's estimate the pixels. It's the nearest background pixel. It's maybe here. So on the hand or on arm, the nearest pixel is very, very small. So the distance is small. At the central region, if it want to go to its nearest background pixel, it even go this way, or this way, or this way. So the distance is larger. So this is another example. If you suppose this is a pixel, and it want to go to its nearest background, it will go this way, or this way. So you can see the distance is slightly larger. If we draw it as a two-dimensional image, it will look like what? So what is application? This is the application. Let me explain. So from this image, there are many, I don't know what's that, cells or plasma. I don't know what that is. Okay, however, when we apply a threshold on this image, we can generate a binary image like this one. Okay, of course, there will be a lot of holes or noise. Again, they can apply some opening and closing method to remove those noise or holes, and then apply the distance transform. So this is a result of the distance transform. And finally, they apply a watershed algorithm so that they can label each cell, so that you can use the method to identify how many cells are in the image. Or if you are interested in the foreground rather than the background, so this is also a way to segment the input image. Okay, then we are talking about a very important concept in image process. It means Fourier transform. Okay, Fourier transform, the concept is we have an image domain, and we want to convert the image domain to frequency domain. So this is a basic concept. And how to convert it? All right. So this is a one-dimensional Fourier transform, and our image are two-dimensional data. But let's see the simplest one. It means because we can represent any signal in cosine and sine. So that's the idea is proposed by Fourier. Fourier is a French mathematician 200 years ago. Okay. So if so, then we can, as you say, if currently we can use computer to do it, no problem. And okay, let's see some example. This is a box filter for one dimensional. Okay, so if we apply the Fourier transform, the decreased form of Fourier transform, we will get the result. And if we draw it, it will like this one. So what's the meaning? So this is the vertical line means the frequency. Here you can see for low frequency, its response is higher. And for certain frequency, the response becomes 0, and for some frequency, its response becomes negative. It means for the box filter, it will preserve most low frequency signal, and for certain signals, it will be removed. And this is another box filter. Okay, it also preserves most low frequency signals, and for linear and bilinear, the set they prefer the low frequency. However, Sobel, we saw Sobel filter so this is one dimension. So -1, 0, and +1. It won't preserve the low frequency signal. It will totally remove the low frequency and prefer certain medium frequency signal. So that is the reason why we see the instance image here. Okay, so where is the low frequency signal? Here on the background, okay, or on the face. There are signals, but they are low frequency. Therefore, they will be removed by the Sobel filter. And where is the signals it will preserve? Just like the vertical edges, it will preserve. And let's go back to where is it? Okay, here. Okay, so this is the corner filter, and let's take a corner filter again. Sorry, corner filter. Okay, so this is the corner filter, and let me enlarge it. Okay, here it will only preserve the high frequency signal. It turns corner. So where is the corner? Around the 4 edges. Okay, and there are some the strong edges. It will preserved by the corner filter. As a result, okay, in the high frequency response, it looks like this. Okay. Low frequency are totally removed. Medium frequency, they are certain, and they prefer or preserve high frequency signals. Okay, so since they are 1D, and there's also the 2D frequency transformation, and there are continuous form and the discrete form. For images, we use this discrete form. And let's show some example. So this is the input image. It is a grayscale because Fourier transform is only handle the grayscale image. So from this image, this is the generated Fourier transform Fourier image. It means there are a lot of low frequency signals in this image. So where is the low frequency? Here, when you see the background, there are many. This smooth. This is low frequency, and there are some vertical and horizontal signals in this image where you can see this is the vertical edges, and this is also vertical edges, and there are some horizontal. Okay, here is also vertical edges, so they present in the frequency domain is the relative brightness along here, and also you can see there is a pattern here. For a certain degree, you can see the slightly larger response. It means in this image, there are some signals, they follow a certain pattern. So what is the pattern? It is the slope. So you can see the edges in a certain degree. Because of the background, you can see many edges at the background. So that is the response along this line. Okay, and then why do we need to care about the Fourier transform? Because we say we use linear filter. When we apply this image with a linear filter, we get the filtered result. And then this step can be replaced in frequency domain. Let's see an example. So when I convert the images to frequency domain, I get this one. And when I convert the filtering kernel into frequency domain, I get this result. And the two, if I, in the frequency domain, I do a pixel by pixel operation. I just sum them up and I will get this result. And I convert the image from frequency domain to intensity domain, I will get this result. Totally the same as this one. Okay, so it means we have signal in the image space. Okay, we see it directly. But however, the data, once it converted to frequency domain, the content of data is the same. And when we apply these approaches, we can quickly generate the result we want. Equivalent applying a linear filter in the space intensity domain. So what can it be used? Okay, so there is a pattern called Moray pattern. Okay, when you take a very close look on your monitor or some printed papers, you will see the pattern. And okay, we can remove those patterns using Fourier transform. This is example. Okay, this is not our textbook. This is another book called image processing using MATLAB. Okay, so I crop. So this is the input image. There are another Moray pattern, and we convert into frequency domain, and because the pattern has a certain specific frequency, we just remove those signals in the frequency and convert it back to the intensity domain. We get this result. If we remove more certain signals in the frequency domain with certain pixel, then we'll get this result. So it works like a denoising algorithm. Okay, this is the real case. Okay, this is the image from NASA. It's taken in 1966. Okay, so you see a lot of patterns here. Okay, it's a vertical pattern because 70 years ago and 60 years ago, the sensors or those devices, this is the limit. But after applying the Fourier transform, okay, say this example, if you see many patterns, diagonal pattern here, if I convert it to a frequency domain, you can see there's a very high response. And if I remove just the two response and convert it to the intensity domain, I will get this result. Yeah. So, but however, this is a synthesized image. This is not the real case. Not real case. Okay, but however, let me show you a real case. Okay, so this is the input image, and I converted it to high frequency domain and apply a high pass filter. Okay, then this is a filtered image. So it's very difficult to. The only difference is only the central part. So you can see there are more red here, but there is less red here. Then I can get a high frequency signal. And if I apply the high frequency by a factor of 3, I will get this result. Okay, let's show a live demo. Okay, so this is the so this is the X-ray image. Oh, sorry, I should not. Let me show. Okay, so this is the input image, like this one. Okay, then I here apply. Okay, so I load it, and here I transfer it to the frequency domain. Okay, and I draw it. So let me just run it and wait for a while. Okay, so this is the input image. Okay, now it is converting the image to the frequency domain. Okay, then I get it, right? So this is okay. There are too many images here. So because the image is not a square, so I crop the square region, and then I apply the. Okay. Oh. Okay, so what I want to say, high frequency, difficult to use. Okay, so this is high frequency signals I checked from the image, and apply it back. I get the result like this. Okay. And so this is original one, and this is the enhanced one. Okay, so the enhanced one for some people it is useful. Okay, but you can see there is a logo. It is also enhanced. Okay, fine. Now, because we are going, some of you may choose to do a mini project. So let me introduce some widely used tools for computer vision. The most famous one is the OpenCV library. Okay. The OpenCV is a very long-standing library because you see it was released in 2000. And it supports many languages and many platforms, and it can do many different things. Okay, and there are a lot of books available either online or in our library. You can download it or borrow it. There are abundant of resources to learn how to use OpenCV, and there are a lot of online videos, etc. See, for this video, there are 9.5 hours. Okay, so if you want to learn, no problem. But however, I think you are busy. Okay, and let me talk about the limitation of OpenCV. Because it was released or developed 20 years ago, so it's very difficult to find the state-of-the-art algorithms in the library. It can solve many problems, but in the state-of-the-art. Okay, so let me show you an example. So suppose this is image, and I want to remove this background pedestrian. OpenCV, yes, it provides a feature called inpainting, and you can easily find some online tutorial for how to use OpenCV's inpainting algorithm. Okay, and how to do it? Just create a mask. So I use the OpenG, this is GMP, to create the mask, and just use 3 lines, you can call OpenCV. Okay, so this is, I load the image, and I load my mask, and I apply OpenCV's inpaint method. So I need to specify first a parameter, how large I want to inpaint. And there are 2 choices for the algorithms. One is Taylor, and another is, okay. So OpenCV provides 2 algorithms. One is the naive, another is Taylor. So you can see both of them were published 20 years ago. Yeah. But if you see the two examples, yes, it can solve some vision tasks, but for us, not very good. So let's try for the first NS algorithm. If I try different radius, 3 by 33, so these are the generated result. Looks cool. And if I use another algorithm, Talia, all right, and I try different parameters, okay, it gradually remove the background pedestrian, but still not good. So what is the good? So this is the result. I manually set the parameter. So what is the beta algorithm? Yeah, there are some beta algorithms in NERFs. So see again, we see this conference NIPS. Now it's called new IPS. Okay, where do I see it? Let me recall it. Here. So this is a new IPS. And what's the relationship between our computer vision? So let's see here, algorithm. Because this is a conference focusing on neural networks, right? So this is a NERD IPS. And let's go back to our example. Yes, okay. So this paper was published in NERD IPS. It is a method of implanting. So this example, if this is input image and it need to implanting those regions, it means all of them, you don't know the content of it. But after applying their method, yeah, this is their reconstructed image. Looks good. Okay, and where can I find an implementation of this method? OpenVINO. Okay, so OpenVINO was a library released by Intel. Okay, so you can find, okay, they implemented it. So if I just use OpenVINO for my task, all right, so this is the result. If I just call the OpenVINO library, so let's compare. This is the input image, and this is the OpenVINO's result, and this is Talia's result. So this, yes, looks much better than this one. Okay. And there are, so the paper proposed by Wang is in 1918, and now it's 2024, so there are a gap of 6 years. There are more new implanting papers. So again, you can just choose one for your final presentation from the CBF Foundation Open Access. And there's another library, free, totally free, and very popular right now. It's called MediaPipe. It was developed by Google, and it was designed for mobile devices, so it runs very, very fast. And there are many SOTA and state-of-the-art algorithms, and it can even run on a website. So let's take a look at it. Okay, so now you see my laptop. Okay, so this is the hand landmark detection. So you can see my hand landmark here. Right, okay. And there are many other choices. For example, gesture recognition. They can capture some simple gesture. So you see. So this is none, sum up, and sum down. Okay, etc. And also there is object detection. Let me see. Person and cell phone. Okay, yeah. So okay, and face recognition. Time? Oh, time? No. Okay, fine. Fine, and face recognition, face detection. Yeah, here. Okay, face detection. Oh, take a look at here. If I rotate my face, it can still detect it. It looks quite good. Here, up, and down, and rotate. Good. So this is state of the art. And the algorithm is blaze face. Okay, it was a paper published in 2019. Okay, 5 years ago. And if you want to know, okay, what the blaze face is, you can go here in my course website. This year, okay, we just talk about the media pipe head. Okay, the one you look, and I also cover blaze face there. Okay, so let's go back here. This is very useful if you want to do a mini project for your presentation. And okay, let's compare. Because OpenCV also has the face detection algorithm. It is a Viola and Chang. So let's just stop here. Stop. Okay, and let's show the result of OpenCVs. Okay, so this is example. They use a cascade classifier to detect faces. So the code is very simple. Load the XM file. In fact, it is a set of classifier, and just run it. Okay, so this is OpenCV's result. Okay, so again, let's pay attention to the limitation. If I rotate my face, well, it doesn't work. And if I not work. And if I rotate my face, it cannot detect. Okay. So yeah, so there's a difference between OpenCV and the media pipe. OpenCV here, the paper, the Viola and the Chang's paper, it was published in 2021. 2001, 23 years ago. Yeah, so you can see. Okay, if you want to use the state-of-the-art method, try OpenVINO or media pipe. If you just want to try some, I should say, solve some problem, OpenCV may work because it's very simple to use. Okay. So let's go back to our slide. Okay, so this is the limitation of face detection of OpenCV. A late report. Okay, in Viola and Chang's paper, late report. Yes, there is the limitation. They know it. Because of what? Because of their ADA boosting, I should say, their classifier, they use ADA booster to do it. And in their training set, they don't have training images greater with those degrees. But for media, sorry, what happened? Okay. For the blaze face, they use SSD. SSD is a object detection algorithm. And MobileNet. MobileNet is did you know? Do you know MobileNet? Is it mentioned in your? Okay, it is a approach to reduce the computational load. Although it slightly reduces the performance, but okay, because as I said, Google they have the Android system. They very care about the market share, so they need to improve the performance. I should say, give some features of their Android devices. So MobileNet is developed by Google too, and the FPM is a feature pyramid network. This is a network architecture, and the focal loss is also an approach to improve the detection rate for difficult objects. Therefore, they combine everything together, become the medium, and very useful for you. Okay, so do you have any question? Okay, if no, then that's the end of our course. Thank you for your participation.